Hello, everyone. Good morning. Good afternoon. Today I will continue on the previous lecture. Now I believe you have most of the resources available with you on Moodle, and also the previous lecture was uploaded on the YouTube, so you can access it no matter. Now I will start from the hyperbola. If you remember in the previous session, we had an introduction about the analytic geometry and how to go through it. We started from the Cartesian coordinates, the relation of a straight line, the distance between 2 points, and all the background that you already know. Then we did go through circle and the ellipse, with the ellipse equation with all of its details, all the various relations between the semi-major axe and the semi-minor axe, and all the relations. What's really very near to the ellipse is the hyperbola. And the hyperbola, it's a movement from the point of view. It is a movement of a point that moves freely in the XY plane, but just keeping that the distance or the ratio between the distance between a point and the focus and divided by the weight and the directrix is constant value, and it is more than 1. This is the eccentricity of a hyperbola. So once more, for a hyperbola, you will have E is greater than 1, and the E stands for PF divided by B of D, where this is the distance between any point on the hyperbola and the focus, and BD stands for the distance between the hyperbola and the directrix, as you will see within the coming slides. Also, anyone can say that the hyperbola, if you have a vertical plane, it will cut the hyperbola into, the hyperboloid or the cone, it will cut the cone into an upper and a lower two parabolas, which represent the equation of the hyperbola that we will go through it shortly, inshallah. So this is mainly the shape that we are talking about, which is the hyperbola. As I told you, it's really very near to the equation of the ellipse. So if you remember the equation of the ellipse, it was like x squared over a squared plus y squared over b squared equal 1. That's for an ellipse with an origin as its center. For the hyperbola, the equation will be x squared over a squared minus y squared over b squared equal 1. And that's the equation of a hyperbola. So the only difference between an ellipse and a hyperbola in the equations is the sign between them. Of course, A is the semi-major axe, B is the semi-minor axe. If you remark here, for B, it's going to equal to A squared times E squared minus 1. Remark also that E here is greater than 1. So within the ellipse, it was A squared 1 minus E squared, because E and the ellipse is less than 1. The origin is 0, 0. This is going to be F stands for the focus, L directrix. For C, A, E, it's A squared plus B squared. In the ellipse issue, it was A squared minus B squared. Of course, L, it's A over E. A over E. Same relation exactly as ellipse. Also, the tangent y equal mx plus c. For here, the condition for tangency is a squared m squared minus b squared. Over there in the ellipse, it was a squared m squared plus b squared. Other than that, there is no difference. The general equation of an ellipse, also if you remember from the previous session, the general one, it is x minus alpha to the power of 2 divided by a squared minus y minus theta to the power of 2 divided by b squared equal 1. This is for an ellipse. If I want to have it for a hyperbola, it's gonna be with a negative sign. Of course, the center here for a hyperbola, it's gonna be alpha and beta, and this is the center for a hyperbola. You will see this also within the coming slides. Okay, so for the next one, here's, as I told you, this is the equation, x squared a squared minus y squared b squared equal 1. The symmetry is about what? In all times, the shape of the hyperbola will be symmetric about the x with a negative sign. This is, if it was written like this, so it's gonna be symmetry, but with respect to the x-axis. I mean the two parabolas. Also, if you want this equation equal to 0 instead of 1, you will get the equation of the two asymptotes that govern the wings of this hyperbola, as you will see. Also, if you remember in ellipse, we have a condition that will help you to, or force the moving point to be an ellipse, which is the sum between the two foci is a constant number. Here the difference between the two foci, it's gonna be constant. So Pf minus Pf dash equal to 2 of A. Okay, if I want to graph or give a sketch for a hyperbola, let's say the equation of the hyperbola that we are going to deal with is x, let me write it here, is x minus let me deal with the standard case where the origin is the center of this hyperbola. So if I have x squared over a squared minus y squared over b squared equal to 1, how to graph or how to sketch, to give a sketch for this hyperbola. The process is really very simple. All I have to do, this is the main axis. So actually, this is the major axis or the transverse axis. For this case, the symmetry will be around the y-axis. So this is the main axis, as I told you, or the transverse axis. Okay, this is the second axis, which is gonna be the y-axis, which is, sometimes we call it the minor axis. So this is the main one, and that's the minor one. The second step, I will go for a square and take a square root for this value, which is gonna be a, and then I will put the points as the following. First of all, from the center to the vertex, then from the center to the focus, from the center to the directrix. Because the directrix is in a hyperbola, it is inside it. So here is the points. Here the center, which is 0, 0. Then you will have the vertices of the hyperbola, which is A and the A dash. And also you will have M and the M dash, where M is the point of intersection, between the directrix and the main axis. Also M dash same way like. And these are the focuses. The distances will be like this. I will start with b squared, taking the square of this value, going up a p and going down a p. This is what I did. This is p, and in this manner I will determine the b dash and the p, or the points mainly for semi-minor axis. So once more, I've drawn the main axis and the minor axis. The minor axis is the axis with a negative sign. Then I will start with P, going up and making just a horizontal line, as I told you, this horizontal line, and going for negative V and doing the same. So this is the second line, so I'm going a rectangle. I will go to the left with the A element, not A square. I will take its square root, so I will go for A right and for A to the left. I have a rectangle. If you look to the distances, I will just write them and I will remove them. So from here to there, this is A. And also the same, from here to here, it is A. This is B, and that is also B. So I'm taking B up, P down, A to the right, A to the left. You can rap about it. Okay, now I've did all this, I have this rectangle. After doing this rectangle, I will use my roller in order to connect the diagonals and extend them as you will see. So these are the two asymptotes that I'm telling you about. So once more, all I did is just drawing the rectangle, B up, B down, A to the left, A to the right, which are the semi-major axe and semi-minor axe. Then I will get the diagonals from the left and from the right. These are the two asymptotes, which are actually, you can find them by connecting these diagonals. Okay, now I will start to put the distances. This is the A distance from the center to the vertex. A over E, which represent the directrix. A times E, which leads to the focus. And I will start to put all of this. So, here's the first directrix. Okay, directrix number 1. Here's the second directrix, directrix number 2. Now I am ready to draw the hyperbola. The hyperbola will come with wings parallel or very close, very close to the asymptotes, making the vertex over here and going down, and the same to the other side. So these are the equation of the asymptotes. This is a point B. If you get a point on the hyperbola, getting the distance BF divided by BD, it's going to be E and greater than 1. These the distances that I told you about. Of course, if I'm dealing with this focus, this is its directrix. If I dealt with F, this F, so this is its directrix. And here is an example of dealing with this directrix and with the point of the focus. Now I can see here is the hyperbola. So actually my hyperbola is the curve that's move beside these two asymptotes, and of course these are the two vertices. For any hyperbola, there is a conjugate hyperbola, which has exactly the same equation, but with negative sign. So it's gonna be x squared over a squared minus y squared over b squared, but equal to -1. And this is what's called a conjugate hyperbola. And the shape of the conjugate hyperbola will be running here to B and similarly like, okay, here is that the hyperbola, as I told you, is negative sign, and this is the shape of the other hyperbola. If you take a good look for the hyperbola, it's really a very nice shape showing everything. Now, once more, I need to read that with you. So, once more, if I want to draw the hyperbola, all I have to do is to go for the equation, determining its minor axe and major axe. I will start, as I told you, this is x, this is the main axe, once more, that's the minor axe. So, this is the equation. If it was like this, I would start by taking square roots and identifying the semi-major axe, semi-minor axe. For the semi-major axe, I will go A small to the left and to the right, making two vertical lines. Then B up, B down, making two horizontal lines. I will get a rectangle. This is what happens exactly. Here is the rectangle that I'm telling you about. Then I will connect the diagonals, as you can see. After connecting the diagonals, I can draw easily the equation of the hyperbola, which is going to come like this, going through A and vice versa. On the other side, it's going to be the same. We move like this, coming near A, and that's the hyperbola that we are talking about. The conjugate one, it will go for the other direction. Let me use my blue pen with it. So it will come also exactly the same, very close to the asymptotes touching, then going up on the other side. In a similar manner, it will come like this, and that's the equation of the conjugate hyperbola, as I told you. In a similar manner, if you want to see again once more everything, all the details, and how to draw all of this, it's really very simple. Just in seconds. Okay, here we go. So these also, as the distances, as I told you about, these are the two directrices, and here is the point, the distances between the focus and the directrix. Once more, if I dealt with this focus, this is going to be its directrix. If you decide to use this point with this focus, this is going to be its directrix. So the directrix, which is relative to a focus, is the nearest vertical line to it. Then I will have my hyperbola, as you can see, and also here is the conjugate hyperbola. This is the distance for x and distance for y. If I have the equation, I can get the coordinates, or the x. If I know the x, I can get the y, as you see. Of course, this is used with plenty of applications. One of the very famous applications is some like this. The cooling towers for nuclear power plant have a hyperbolic cross section. Also, if you sit near a lake or something and you have two stones and you threw them into the water, these are the intersection of the waves generated, which can be connected to each other, giving you also the shape of a hyperbola, as you can see. One of the standard problems is a quadratic equation, and you want to know the shape which this equation represents. So all I have to do is to try to either put it on the form of a hyperbola or ellipse, or making it near one of these equations, and then you will be able to determine the type of this equation. So if I want to start to make the perfect square, in order to be able to determine the shape and the type of this hyperbola, all I have to do is to get the x values near to each other, the y values near to each other, as you know. Then I will try to make completing square. So I will take a common from the x components. I'll take 16, so it will leave me with x squared minus 2x. Similar manner for y squared, but I have negative sign. If this sign is positive, you will have an ellipse. But this sign is negative, so it will lead to a hyperbola. So I will take negative 25 as a common from the third and fourth terms, as you can see, and you will have negative 484, and that's the constant. Now I can start making my square roots, or the perfect, or completing the perfect square. Once more, if you forget about this, all I have to do is to write 16, open your bracket. Inside it, I will make a bracket to the power of 2. From x squared, I will take an x. Negative 2x, I will divide this number by 2. So it's going to be negative 1. Once more, try to expand it. First to square x squared, per second times 2, negative 2x. Last square is positive 1. So I will add negative 1. In a similar manner for the other part, it's going to run exactly the same. So it can be easily y plus 2 to the power of 2. So the first square y squared, first second times 2, which is going to be 4y. The last one is 4. So I will put negative 4, as you can see. Now in this manner, I will let the negative 25 to be multiplied. First by y plus 2, second by negative 4. And voila, that's what you are going to have. 16 times x minus 1 to the power of 2. Minus 25 times y plus 2 to the power of 2, and these are the numbers that we are talking about. 100 minus 484 minus 16. I will gather these numbers all together and send them to the other side, which is going to be a 400. Dividing on the 400, this is the optimal equation. As you can see, this is an equation of a hyperbola. An equation of a hyperbola with A small equal to 5. Now I have B small, which is 4. The center of this hyperbola, it's gonna be a 1 and a negative 2. If you want to get the eccentricity, it's really very simple, because it is C squared equal to A squared plus B squared. So all I have to do is to get these values, and it's gonna equal to A times E. So C is gonna be the square root of A squared, which is 25 plus 16, both together, and the C will equal to the root of 41, I believe, and the E will be root 41 divided by 8, which is 5, a value that exceeds positive 1 if you are interested in finding or determining this value. From all of this, now I have the E, the equation, and above all the center, which is 1 and negative 2. Now I can construct my hyperbola simply, as you will see. Okay, now once more, here are everything, the E, the A, the B, the alpha plus B, all the points, everything. Please do check it, it's really very simple. Okay, now I want to graph this equation. So I will go for the x-axis and y-axis. Then I will try to go for the new y-axis and x-axis, which are here. I will go for 1 and the negative 2. So actually, this is the new center. This is the new center of the hyperbola. And from here, I will start to draw everything. So this is 1 and negative 2, which is the center of this hyperbola, as you can see. The second step, this is y and x. These are the points relative to s, which is 1 and the negative 2. And all of these points we can determine. As you can see, this is 16. Get the square root, which is 4, 17 minor x. I will go 4 and up, 4 and down. I will try to draw, as I told you, the rectangle that I'm telling you about. 5 to the right, 5 to the left, which are the vertices. I will connect the two diagonals, which are the asymptotes of our parabola. A is 5, A over E, A times E stand for the distances from the vertex to the directrix, or from the vertex to the focus. Here's the directrixes, directrix 1 and directrix 2. And here are the focuses. These are the main equations. Simply you can get them by making the equation to be on the form x minus 1 to the power of 2 divided by 25 minus y plus 2 to the power of 2 over 16 equals 0, and try to solve to get these equations together. So it's going to be x minus 1 over 5 will equal to y plus 2 over 4 was a positive or negative, and so it will give you the equations of the asymptotes. Here is your parabola as it should be done. Okay, this is all about the hyperbola and all about the graph issue and everything. Okay, a tangent of a hyperbola, as I told you previously, it's going to be almost the same condition. C equal to a square m square, but instead of plus b square in the case of the ellipse, it's going to be minus b square. Also, the points of contact, it's going to be the same, negative b square m over c, but in the hyperbola, it will be negative b square over c. Remember, in the ellipse, it was a positive b square over c. So, this is the equation of the tangent. Now, I want to talk with you about the parabola, which is really very famous with plenty of applications in engineering in general. The parabola stands for the equation of a second degree, and also can be defined from the concept of the analytic geometry as the locus of a point that's moving, where the distance between the point and the focus divided by the point and the directrix equal to E, and it is 1. Once more, here is the shape of a parabola. If this is the focus, so the distance from the vertex to the focus equal the distance from the focus till the directrix. If you have a P, any point on the parabola, and you get PF divided by BD, you will find it equal to 1, and this is the shape of the parabola. Usually, I depend on this equation. It is usually symmetric about the x, which is not with power 2. So this equation, for example, for this shape, it's gonna be symmetric about the x-axis. So actually, the equation will be y squared equals some value. I would like to put it in this form, 4 of a times x, or 4 of b times x. Where 4 of a, it's called sometimes the lotus rectram, or it's called, it is 4 times the distance between the vertex and the focus. Sometimes we write it like this. Of course, the parabola doesn't have a center like the ellipse or the hyperbola. Both of them, they have centers, and they will be written based on these centers. But in the parabola case, it doesn't have a center, but we will use its vertex as the main point that I will use in drawing such a parabola. Here the directrix in the line, as I told you, x equal to negative b. This is for y squared for b of x, exactly like what I wrote to you. And this is the case I want to show you. For this one, the vertex will be the origin. So I'm going to drive x-axis, and this is going to be the main x, y equal to 0. It's the x of symmetry. And you will have y, and of course it's symmetric about the x with no, so it's symmetric about the x-axis. If this number is 16, 64, whatever, I will divide it by 4. Taking b left, b right, which is going to determine the focus. So p to the left, p to the right. Now I have the focus and I have the directrix. This line is the directrix, and this is the main x, and the vertex is 0, 0. This is the point of the focus, which is p and 0 on the positive side, of course. Okay, this is the shape of the parabola. If you get PF by BD, it's gonna equal to E, and it is 1. For all of this distance, it's called the focal chord or the lotus rectram, and it is 4 of B. Remark, same equation, it's exactly the same equation, but if, for example, if you have negative 4p of x, the parabola will be on the other side. I will show it to you in the coming slide. And if it was x squared equal 4b of y, so it's going to be symmetric about the y-axis, and actually this is going to be the case. And the equation for this guy is going to be, as you can see, x squared equal 4a of y, because it's symmetric about the x with no power. So this symmetry here is going to be about the y-axis, as you can see. Since this sign is positive, so it's open upward. If this sign is negative, it's going to be open downward, and the directrix will be, the shape will be actually the reciprocal or the inverse of this guy. So this is once more the equation as I told you about. In graphing, a parabola is symmetric about the log squared the x. This is the general case of an equation of a parabola where you have x, the vertex is going to be h and k in the case of a parabola. This is the shape. Okay. In case of horizontal x, this is going to be, as you can see here, it's symmetric about the y-axis because it doesn't have a square. Here it's symmetric about the x-axis because it is the x that's doesn't have a square. Axis of symmetry, this is y squared for a of x. So this is the parabola, and it is open in the a direction. If this sign is negative, it's going to be on the opposite sign. So this is y squared minus 4ax. This is the case of of having x squared equal 4 of ay, so it's going to be upward. And of course, it is negative 4ay, it's going to be downward. All the details and everything you will find in the next slides. Okay, perfect. Now I want to talk with you about some of the famous conics. I will summarize what we did go through. This is from the slides in Lisbon. So any circle, the general case is going to be x minus h to the power of 2 plus y minus k to the power of 2 equal r squared. And you already know that. For any ellipse, okay, for any ellipse, so it's going to be x squared over a squared plus y squared over b squared equal 1. Remark, one of the most important remarks. A stand for the semi-major axis. So here in this case, you have A is greater than B. This is why the ellipse is taking his eggy shape or this ellipsoidal shape, but with respect to y. If you remark, this is positive A and negative A for the A values, and for here it is B and that's minus B. Of course, if you want to get the eccentricity or the focus or whatever, you can do all of this. Of course, here's major x is equal to 2a and the minor x is equal to 2b. This is the other case where a is larger than b, but a actually it is x squared over a squared, and in this case the bigger number is under a, so you will have your ellipse in the x direction. So regardless, a small stands for the major x. If it was under the x, so this is going to be the major x. If it was under the b, under the y, I'm sorry, so y will be the major x. That's a brief about the hyperbola and the conjugate hyperbola. This is the case where x squared over a squared minus y squared over b squared equal to 1. So this is actually the hyperbola that we are talking about. Remark that the axis of symmetry is around y here because it is the axis with negative sign. If I multiply this by negative, I will get the conjugate hyperbola, and this is going to be the case. Of course, you have the similitudes and everything. Okay, perfect. These some remarks about the hyperbola, and we already did say it and did go through it. The hyperbola has two foci and their coordinates fc and f dash negative c. Remark that the c is a squared plus b squared as I told you, and in the ellipse it's a squared minus b squared. Center of hyperbola, the midpoint of the line joining the two foci or the two vertices for a hyperbola. The points where the hyperbola intersects the axes are called the vertices. Transverse axis, this is the major axis. The conjugate axis is the axis where the symmetry is about it. Okay, here's the parabola, which is y ax squared plus p of x over c, which is the general case of a second degree equation. If you put it on the normal form, simply you will make a complete square of something. You will get the vertex of this parabola. Really very simple. If you want to see these steps, it's very simple. So all I have to do, if I have y equal as this problem, x squared minus 2 over x minus 3. So all I have to do simply is to make it y equal 2 to the power of 2. This is x. I will take negative 1, and this is negative 3. So x squared is going to be first, second times 2 negative 2x. The last is going to be positive 1. I will insert negative 1. So the general equation will be y, which equal to x minus 1 to the power of 2. And negative 1, negative 3 is going to be negative 4. That's moved to the other side. This is the general equation that we are talking about. So I will go for x at 1, and then I will go down to negative 4. This is the vertex. The sign is positive, so it's going to be upward. If you want to get where is the focus, it's very simple. The focus is going to be, I will consider this number, which is 1, divided by 4. So it's a 1 over 4. So I will go from here, going up to 1 over 4, which means that I am on the y-axis, at negative 3.75. And this is the focus of this parabola. If you want to get the equation of the directrix, all you have to do is to go down for another 1.4. So actually, this is the directrix equation, or the line, and it is at negative 4.25. This is what's all about, all the ideas, all the laws relative to the quadratic equations, the parabola, the hyperbola, or the conic sections of the story in general, the hyperbola, and the ellipse with all the details connected to all of them. I'm sorry, I will have to clear the screen in order to have everything clear for you. In the coming lecture, I will go with you through the stuff in 3 dimensions, and we will be talking about this marvelous shapes. We will go through this next lecture, inshallah. We will know about the hyperbola of 1 sheet, the hyperbola of 2 sheets, the ellipsoid. So keep tuning, and inshallah, in the next lecture, we will go through all of this, finish this chapter, and hopefully I will be able to go through coordinates. Thank you very much. I appreciate your time, and I'm very, very happy to be with you today. Thank you. Enjoy the rest of your day. Thank you.